Welcome to this video, where we'll tackle the problem number 813, largest sum of averages. This is an exciting problem that challenges our ability to think about dynamic programming and optimal splits in an array. Let's dive into the details and explore the best approaches to solve it. The problem asks us to maximize the score of splitting a given integer array, nums, into k non-empty contiguous subarrays. The score of a split is defined as the sum of the averages of each subarray. For instance, if we split the array into 3 parts, we calculate the average of each subarray and then sum these averages to find the score. Our goal is to find the maximum possible score for any valid way of splitting nums into k subarrays. The input consists of the array nums, or its length is between 1 and 100, and its elements are positive integers up to 10,000. Additionally, k is an integer between 1 and the length of nums. The output is a floating point number representing the maximum score, and answers within 10 to the power of -6 of the correct value are considered valid. To understand this better, let's look at the first example. Here, nums is 9, 1, 2, 3, 9, and k is 3. The optimal way to split this array into 3 subarrays is 9, 1, 2, 3, and 9. For these subarrays, the averages are 9.0, 2.0, and 9.0, respectively. Adding these averages gives us a total score of 20.0. This is the maximum score achievable for this input. In another example, if nums is 1, 2, 3, 4, 5, 6, 7, and k is 4, the maximum score is 20.5. The specific explanation for this example is described next. In the second example, one optimal way to split the array is 1, 2, 3, 4, 5, and 6, 7. For these subarrays, the averages are calculated as 2.0, 4.0, 5.0, and 6.5, respectively. Summing these averages gives us a total score of 20.5. The problem also has various constraints and edge cases to consider. For example, if k is 1, the result is simply the average of the entire array. If k equals the length of the array, each element forms its own subarray, and the result is the sum of the elements. Additionally, if all elements in the array are the same, the result depends on the value of k. It's also important to handle extreme values, such as when the array or its elements are at their maximum allowable sizes, to ensure the solution is efficient and accurate. To solve the largest sum of averages problem, one straightforward approach we can consider is brute force. The intuition behind this method is to generate every possible way to split the array into exactly k contiguous subarrays, calculate the average of each subarray, and sum them up to find the maximum score. While this method is simple to conceptualize, implementing it involves recursively generating all possible partitions of the array, which means the number of combinations grows exponentially. Specifically, the time complexity of this approach is k*2 to the power of n, where n is the size of the array. This makes brute force computationally expensive and impractical for larger inputs, especially when n can go up to 100. Instead, we can adopt a more efficient solution using dynamic programming. The key idea with dynamic programming is to break the problem into smaller subproblems. By recognizing that the maximum score for splitting the array into k parts can be built incrementally from the scores of splitting smaller prefixes into fewer parts, we can reduce the redundant calculations and achieve significant performance improvements. To implement the dynamic programming approach, we use a recurrence relation that builds the solution iteratively. The recurrence is defined as dp I k equals max dp j k1 plus average nums j plus 1 I for all j less than I. Here, dp I k represents the maximum score for splitting the first I elements of the array into k parts. This relation allows us to compute the optimal solution for I elements using the solutions for smaller prefixes. To efficiently calculate averages, we pre-compute prefix sums, enabling quick access to the sum of any subarray. The implementation involves setting up a 2D dp table where dp I k stores the maximum score, and we use nested loops to iterate over the number of splits and the possible subarray boundaries. While the time complexity of this approach is k*n squared due to the nested iterations, and the space complexity is n*k for the dp table, it is significantly more efficient than brute force and works well within the problem's constraints. This makes it a practical solution for n up to 100 and k up to n. By leveraging prefix sums in the dynamic programming approach, we further optimize the computation of subarray averages, which is a critical operation in this problem. While the DP approach does require k space, this is manageable given the problem's constraints, where k is at most 100. The key insight, or the aha moment here, is recognizing that the problem can be broken into overlapping subproblems. The optimal solution for the first I elements depends on the solutions for smaller prefixes, allowing us to build the solution incrementally. While brute force was ruled out due to its inefficiency, no other strategies, such as greedy methods, can guarantee an optimal solution due to the nature of this problem. In conclusion, the dynamic programming approach strikes the right balance between performance and simplicity. It effectively reduces redundant calculations, ensures correctness, and operates efficiently within the given constraints, making it the most practical solution for the largest sum of averages problem. To solve the problem of maximizing the sum of averages when splitting an array nums into k contiguous subarrays, we need to break it down systematically. First, consider a brute force approach. The idea is to generate all possible ways to partition the array nums into exactly k contiguous subarrays. For instance, if the array has 4 elements and k is 2, we could split it into partitions like nums 0, nums 1, nums 2, nums 3, or nums 0, nums 1, nums 2, nums 3, among others. Once we have these partitions, the next step is to calculate the average for each subarray. The average is just the sum of the subarray divided by its length. After computing the averages for a partition, we add them together to get the sum of averages for that specific split. As we evaluate all possible partitions, we track the maximum sum of averages encountered. Finally, once all partitions are processed, the highest sum of averages is our result. While this brute force method is intuitive, it's computationally expensive, so we need to explore optimizations. The brute force approach relies on 3 main steps. First, we enumerate every possible way to split the array nums into exactly k contiguous subarrays. This ensures that all potential configurations are considered. Next, for each of these partitions, we calculate the average for every subarray. The formula for the average is straightforward, it's the sum of the subarray divided by its length. Once we compute these averages, we then sum them up to get the total for that specific partition. As we handle each partition, we keep track of the maximum sum of averages seen so far. Finally, after examining all possible partitions, the result is the maximum value obtained. However, this exhaustive approach has a significant drawback. As the size of the array grows, the number of partitions increases exponentially, making the method impractical for larger inputs. Now, let's delve into some key insights for optimizing the solution. First, the requirement to split the array into contiguous subarrays is critical. This ensures that every element of the array is used exactly once, which simplifies the problem and reduces the potential number of partitions compared to arbitrary subsets. However, this constraint also introduces a challenge. Directly enumerating all possible splits is computationally prohibitive because the number of partitions grows combinatorially with the size of the array. Furthermore, repeatedly calculating sums and averages for every subarray adds additional overhead. We also need to account for edge cases. For instance, if k equals 1, the entire array is treated as a single subarray, so the result is simply the average of the whole array. If k equals the size of the array, each element forms its own subarray, and the result is the sum of the elements. Additionally, arrays with 0 or negative values require careful handling to ensure the averages are calculated correctly. To address the challenges posed by the brute force method, we turn to dynamic programming, which allows us to compute the result efficiently. The key is to use a DP table, denoted as dp, I, j. Here, I represents the first I elements of the array, and j represents the number of subarrays formed so far. The value at dp, I, j, represents the maximum sum of averages we can achieve by splitting the first I elements into j subarrays. Another critical data structure is the prefix sum array. This allows us to compute the sum of any subarray in constant time. The prefix sum array is built such that prefix I stores the sum of the first I elements of the array. Using this, the sum of any subarray from index L to R can be calculated as prefix R, prefix L. These two tools, the DP table and the prefix sum array, are the foundation of the optimized approach. With the dynamic programming approach, the key operation is to compute the DP, I, J value efficiently. To do this, we consider the last subarray ending at position I. The idea is to split the array at some position p where 1 equals p less than I. The subarray from p to I contributes to the average, which is calculated as prefix I, prefix p /IP. Once this average is determined, we update the DP state by taking the maximum of the current value of DP, I, J, and the sum of DP, P, J1, the best result for the previous J1 subarrays, plus this new average. By iterating over all possible split points P, we ensure that DP, I, J, reflects the best possible sum of averages for splitting the first I elements into J subarrays. The final result is stored in DP, N, K, which gives the maximum sum of averages when the entire array is split into K subarrays. Finally, let's analyze the time complexity of both the brute force and optimized approaches. The brute force approach involves generating all possible partitions of the array into K contiguous subarrays. Since the number of partitions grows combinatorially, this method has exponential complexity. Additionally, calculating the averages for each partition requires linear time, resulting in an impractical solution for larger inputs. In contrast, the dynamic programming approach is much more efficient. Filling the DP table involves iterating over all I and J values, and for each combination, we evaluate up to I possible split points. This results in a time complexity of O, n squared * k. Pre-computing the prefix sums takes O, n, which is negligible compared to the DP computation. Overall, the optimized approach reduces the computational complexity significantly, making it feasible for larger input sizes. Here, we begin by defining a class called solution and its method largest sum of averages, which takes two parameters, nums, the input array, and k, the number of groups. The first step is to calculate the length of the input array, which we store in n. We then initialize a prefix _sum array with zeros, having a size of n plus 1. The purpose of this array is to pre-compute prefix sums, which allow us to efficiently calculate the sum of any subarray later on. To populate this, we iterate through the input array and use a running total to fill prefix _sum such that each entry at index I plus 1 contains the sum of all elements from the beginning of nums up to index I. Next, we define a helper function called average that calculates the average of a subarray spanning indices I to j. It uses the pre-computed prefix _sum values to compute the sum of the subarray in constant time, and then divides it by the subarray length. After this, we introduce a dynamic programming table DP, which is a 2D array where DP, I groups, will store the maximum sum of averages for dividing the first I elements of the array into groups. To handle the base case, we iterate through all possible subarrays from the start of the array. When k equals 1, the maximum sum of averages is simply the average of the entire subarray, so we calculate this and store it in DP, I, 1. Now, we move on to handle cases where k is greater than 1, meaning we want to divide the array into multiple groups. To do this, we use nested loops. The outer loop iterates over the number of groups from 2 to k, and the next loop iterates over the possible endpoints I of the subarray, ensuring that at least groups elements exist for the division. Then, an inner loop examines possible positions j to split the array into two parts, one ending at j with groups, 1 groups, and another starting at j with the remaining elements. For each possible split, we calculate the sum of averages by adding the result from DP, j, groups, 1, to the average of the subarray spanning j to I. We update DP, I groups, with the maximum sum obtained across all valid splits. Finally, after completing the dynamic programming table, the maximum sum of averages for dividing the entire array into k groups is stored in DP, n, k, which we return as the result. Here, we start by importing the necessary libraries and defining a solution class with the method largest sum of averages. The method takes an integer array nums and an integer k, where k represents the number of groups we want to divide the array into, to maximize the sum of averages. First, we calculate the prefix sums in the prefix sum array. This helps us efficiently compute the sum of any subarray later on. The idea is simple: each element in prefix sum at index I plus 1 contains the sum of all elements in the nums array up to index I. Next, we define a 2D dynamic programming array DP, where DP, I groups, represents the maximum sum of averages we can achieve using the first I elements of the array divided into groups. Now, for the base case, if there's only one group, the maximum sum of averages is simply the average of the entire subarray from the start to index I. This is why we initialize dp I1 with prefix sum I/I. Finally, we start filling up the dp table for multiple groups, iterating over the number of groups from 2 to k. For each group count, we calculate the maximum sum of averages for subarrays ending at every possible index I. This is done by iterating through potential partition points j, where the last group starts after j. In this continuation, we complete the nested loops by calculating the maximum sum of averages for all valid partition points. Specifically, for each group count and ending index I, we iterate over potential partition points j. At each step, we calculate the average of the last group, which is the subarray from index j to I, using the prefix sum array. We then add this average to the value stored in dp j groups 1, which represents the maximum sum of averages for the previous groups 1 groups. The dp I groups value is updated with the maximum sum found across all possible partitions. Once the dp table is fully populated, we return dp n k as our result. This value represents the maximum sum of averages achievable by dividing the entire array into k groups. The dynamic programming approach ensures efficiency, as repetitive calculations are avoided by reusing previously computed results. We start with the problem setup for the given example where nums is 9, 1, 2, 3, 9, and k equals 3. Our goal is to partition this array into 3 groups in a way that maximizes the sum of the averages of these groups. The first step in solving this is to pre-compute the prefix sums, which allows us to quickly calculate the sum of any subarray. For this example, the prefix _sum array becomes 0, 9, 10, 12, 15, 24. Next, we initialize the base case for k equal to 1. If we can only have one group, the best we can do is calculate the average of the entire array up to each index. Using this logic, we compute dp values for k equals 1 as dp 1, 1 equals 9.0, dp 2, 1 equals 5.0, dp 3, 1 equals 4.0, dp 4, 1 equals 3.75, and dp 5, 1 equals 4.8. These represent the maximum average sums for one group. The next step is to compute the dp values for cases where k is 2 or 3. Now, we move on to filling in the dp table for k equals 2 and k equals 3. For k equals 2, we consider splitting the array into 2 groups and iteratively calculate dp I2. For example, dp 2, 2 is calculated as dp 1, 1 plus the average of the subarray from index 1 to 2, which results in 10.0. Similarly, dp 3, 2 is the maximum of 2 scenarios, splitting at index 1 and splitting at index 2, which gives a value of 11.0. Following this logic, dp 4, 2 becomes 12.67, and dp 5, 2 becomes 14.67. Then, for k equals 3, we add an additional group. For example, dp 3, 3 is calculated as dp 2, 2 plus the average from index 2 to 3, giving 12.0. Using similar calculations, dp 4, 3 becomes 14.0, and dp 5, 3 reaches 21.67. Therefore, the maximum sum of averages for this example is 21.67 when the array is partitioned into 3 groups. In this second example, we consider nums as 1, 2, 3, 4, 5, and k equals 2. The goal is to partition the array into 2 groups to maximize the sum of the averages. We start by pre-computing the prefix sums, which results in the array 0, 1, 3, 6, 10, 15. This helps us quickly calculate subarray sums later. For the base case where k equals 1, the maximum sum of averages is the average of the entire array up to each index. Using this approach, we calculate dp 1, 1 as 1.0, dp 2, 1 as 1.5, dp 3, 1 as 2.0, dp 4, 1 as 2.5, and dp 5, 1 as 3.0. These values represent the maximum sum of averages when the array is treated as one group. Next, we begin calculating dp values for k equals 2, where the array is divided into 2 groups. To calculate dp for k equals 2, we iteratively compute the maximum sum of averages for two groups. For instance, dp 2, 2 is calculated as dp 1, 1 plus the average of the subarray from index 1 to 2, resulting in 3.0. For dp 3, 2, we evaluate two possible splits, one at index 1 and another at index 2. The maximum value between these splits is 4.5. Similarly, dp 4, 2 is the maximum of splitting at index 2 or index 3, yielding 6.0. Finally, dp 5, 2 considers splits at index 3 and index 4, resulting in a value of 7.5. Thus, the maximum sum of averages for two groups in this example is 7.5, achieved by optimally splitting the array into two parts. To analyze the time complexity of the solution, we start by breaking it into distinct steps. First, calculating the prefix sum involves a single pass through the array nums, which has a size of n. This step is linear, with a time complexity of O, n. Next, we initialize the base case for k equals 1, where the average of all subarrays, 0i, is computed for I from 1 to n. Since each average computation takes constant time, initializing dp I, 1 for all I also has a time complexity of O, n. The most computationally intensive part is populating the dynamic programming table. Here, we use three nested loops. The outermost loop iterates over the groups from 2 to k, which contributes O, k. The second loop iterates over indices I from groups to n, contributing up to O, n, per group. Finally, the innermost loop iterates over possible split points j from groups 1 to I1. This can contribute up to O, n, for each I. Within these loops, computing dp I groups involves calculating the average of a subarray in constant time, O1. When all these loops are combined, the total complexity of filling the dp table becomes O, k asterisk n squared. Adding this to the earlier steps, we have an overall time complexity of O, k asterisk n squared, for the algorithm. Returning the result stored in dp n, k, is a simple, constant time operation, O1. When we sum all the contributions, the overall time complexity is O, n, for the prefix sum, O, n, for initializing the base case, O, k asterisk n squared, for the dp table, and O, 1, for the final retrieval. This simplifies to O, k asterisk n squared. In the worst-case scenario, where k scales with n, such as k equals n, the time complexity becomes O, n cubed. Now, looking at space complexity, the prefix sum array requires space for n plus 1 elements, which is O, n. The dp table, being a 2D array of size, n plus 1 asx, k plus 1, requires O, n asterisk k, space. Auxiliary space, used by the average function and other temporary variables, is constant, O1. Therefore, the total space complexity is dominated by the dp table and the prefix sum array, resulting in O, n plus n asterisk k, which simplifies to O, n asterisk k. Comparing this dynamic programming approach to a brute force method highlights the efficiency gained. A naive solution would involve generating all possible ways to split the array into k groups. The number of possible splits grows exponentially, requiring O, 2 to the power of n, time. Additionally, calculating averages for each split would add another factor of O, n, resulting in a total time complexity of O, 2 to the power of n asterisk n. The space complexity of this brute force approach would depend on recursion depth and subarray storage, potentially reaching O, n. On the other hand, the dynamic programming approach avoids redundant calculations by using memoization, significantly reducing the time complexity to O, k asterisk n squared, and the space complexity to O, n asterisk k. This optimization makes the problem tractable even for larger inputs, where the brute force method would be infeasible. The best, average, and worst-case scenarios for this algorithm can be understood based on the value of k. In the best case, where k equals 1, the solution only computes the average of the entire array, leading to a time complexity of O, n, and a space complexity of O, n. For typical cases, where k is much smaller than n, the time complexity remains O, k asterisk n squared, and the space complexity is O, n asterisk k. In the worst case, when k equals n, the time complexity increases to O, n cubed, and the space complexity becomes O, n squared. These complexities are mathematically justified by the use of prefix sums, which ensure that each average computation is constant time, O1. Additionally, the nested loops in the dp table iterate at most n asterisk k times, confirming the O, k asterisk n squared, time complexity. Similarly, the storage requirements for all subproblems in the DP table of size n asterisk k validate the O, n asterisk k, space complexity. When solving this problem, there are several common mistakes to watch out for. First, forgetting to account for edge cases can lead to runtime errors. For instance, if the array nums has fewer elements than the required number of splits k, your solution might fail. Always validate the input size to ensure it aligns with the constraints. Another common issue is misunderstanding whether subarrays must be contiguous or if they can be disjoint. Misinterpreting this can lead to completely incorrect solutions, so always clarify the requirements before proceeding. Inefficient handling of subarray computations is another pitfall. Recomputing sums for overlapping subarrays repeatedly can significantly slow down your program. Using prefix sums is an excellent way to optimize these calculations. Additionally, ensure that all array splits are valid and cover the entire array. Problems often arise when solutions allow too few or too many splits, leading to incomplete or invalid results. Finally, watch out for integer division issues. In some programming languages, integer division can yield inaccurate averages. To avoid this, use floating point division or explicitly cast your values as needed. In interviews, it's crucial to clarify constraints early. For example, ask whether subarrays must be contiguous, whether the value of k can change, or if optimizations, such as pre-computing values, are expected. These details often influence the approach you should take. After describing the brute force solution, focus on discussing optimizations. Highlight methods like dynamic programming or sliding windows, which can significantly reduce time complexity. It's also important to communicate the trade-offs between time and space complexity. For instance, while prefix sums can speed up your algorithm by avoiding redundant calculations, they do require extra memory. Demonstrating thoroughness by testing edge cases will also leave a strong impression on your interviewer. Examples of such cases include an empty array, a single-element array, or scenarios where k equals 1. These steps show that you're not only thinking critically about the problem but also ensuring your solution is robust. This problem shares similarities with several others, making it worthwhile to explore related scenarios. For example, LeetCode problem 410, split array largest sum, also involves dividing an array into k parts but focuses on minimizing the maximum sum. Another related problem is LeetCode 644, maximum average subarray 2, which shifts the focus to finding the maximum average of a subarray without constraints on the number of splits. If you're looking to explore variations, LeetCode 1014, best sightseeing pair, is interesting because it involves optimizing subarray selection for a maximum score rather than focusing on averages. Lastly, LeetCode 53, maximum subarray, is a classic problem that employs techniques like prefix sums or sliding windows, which are highly relevant to solving this challenge. Reviewing these problems can deepen your understanding of the underlying concepts and approaches. There are alternative approaches to solving this problem, each with its own strengths and trade-offs. One powerful method is dynamic programming. Here, you can use a 2D DP table where dp, I, j, represents the optimal solution for splitting the first I elements into j subarrays. This reduces redundant calculations compared to brute force methods but does come with increased space complexity. Another approach is binary search on the result space, which is particularly useful for problems that involve minimizing the maximum sum. By combining binary search with a greedy check to validate each candidate, you can achieve efficient results. Additionally, prefix sums are invaluable for optimization. By pre-computing the sums of subarrays, you can calculate results in constant time during subsequent iterations, significantly speeding up naive approaches. However, each method comes with trade-offs. Brute force is simple to implement but computationally expensive, making it suitable only for small inputs. Dynamic programming strikes a balance between time and space but can be challenging to implement under pressure. Binary search, while efficient, requires careful handling of edge cases and boundary conditions. Understanding these trade-offs will help you pick the right approach for different scenarios. Thank you for following along as we solved the largest sum of averages problem. We covered the key approaches, their complexities, and important takeaways. Remember to practice breaking problems into smaller subproblems and using dynamic programming effectively. Don't forget to like, share, and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!